right, so today we get to actually start talking about what exponential functions are. So we dealt with exponents in the last couple days, but we didn't actually see them as functions or on a graph. It's your hand. 203, I think. Is that right? Yeah, 203. Okay, so first question. We have Mallory, who is a medical research scientist, discovered a new bacteria culture which could help strengthen a person's immune system. To find a growth rate, she isolated 5 cells and...
Good morning, Huntington Hills. Please excuse this interruption. I just want to remind all grade 10 through 12 that you have H team today. There is no flex. You are to attend your H team. We're continuing with the secret passage thing, so it's very important that you go to your H team class during that time. Thank you very much and have a wonderful day.
Okay, so isolated 5 cells and then looked at the growth of the cells. So they give us a little point form version of what happened, and then they also put that into a little table of values for us. So we can see after an hour, there's 10 cells. After 2 hours, there's 20. After 3 hours, there's 40. Mallory concluded that the growth pattern of the culture is, of course, 5 times 2 to the power of t. And we are going to start highlighting now. So the reason I want to do this is because now we have an equation that has 2 variables. This is a word problem where we want to know what those variables represent. So it says t represents the time in hours. So then I'm going to highlight that section, and where I find the t in my equation, I'm going to highlight it. Now, you might be tempted to highlight that little t as well. You don't need to. That entire section there represents the y variable. So we don't need to worry about it. N of t is the entire other variable. Okay. And then it says n of t, which we can highlight that entire thing, represents the number of cells after the t hours. So I'm just going to do number of cells. Okay. So now I know what each of those pieces in my formula represent, and that way I won't forget that. Now, something that we didn't do the last time with word problems that we still don't really need to do now, but I want to get you in the habit of it, is deciding which variable would be your y and which variable would be your x. Because when we put it into our graphing calculators, our calculators use y and x specifically, but oftentimes our word problems use different variables. So your y variable should be the variable that's isolated, and the x variable should be the one with everything else in the equation. So the y and the x represent the n of t and t. Okay, so again, we don't really have to do it in this question, but will help us later on. Then it says determine how many cells there were after 8 hours. So how many cells, that's what I was highlighting in my blue color. And then the number of hours is what I was highlighting in pink. So I'm going to make sure I do the same colors. That will help me keep organized. So now I know really easily that T, which has been the pink color the whole time, is represented by the 8. Okay, I'm trying to figure out n of t from this question. Okay, so there's a couple different ways I can do it. I could look at the pattern in the table of values and just continue the pattern. However, they literally gave me an equation, so I might as well just use the equation. I know the equation has a 5 multiplied by a 2 to the power of t, but we know t is actually equal to 8 in this question, and then you just throw that into your calculator and let it do the work for you. When I put that into the calculator, I get 1,280, and this represents the number of cells, so I'll just write that word after. Questions? Okay, so I know it seems a little bit juvenile, but using the highlighters helps organize your word problems so much better. I found in my first year of teaching 30-2, a lot of my students just had trouble figuring out which thing they were asking for and which thing you had, so this helps with that problem. Part B, it says after 12 hours, there are 20,480 cells. How many hours will it take to double that amount and then have half of that amount? Now, something I want us to recognize before we try and answer that question is every time my number of hours increases by 1. Okay. What happens to my number of cells? So from 5 to 10, from 10 to 20, from 20 to 40, what is that number doing?
Multiplying by 10.
By 2, yes. It's doubling, right? 5 times 2 is 10. 10 times 2 is 20. 20 times 2 is 40. We're multiplying it by 2 every time, or we're doubling it, okay? So in this question, when it says how many hours is it going to take to double that amount, it is literally doubling every hour, okay? I was told in this question that after 12 hours, there's 20,480 cells. So if I want that amount to double, I just have to wait 1 more hour. Every single hour, it is doubling. So I don't need to do a calculation to answer this question. I know that every single hour, my number of cells is doubling. So if I want it to double, I just have to wait 1 more hour. They told me that number was for 12 hours. So if I wait 1 more hour, then I'm at 13. Okay, if I want to have half of the amount, consider that that's just the opposite of doubling. So if I look at my table of values, if I want half, then I'm just going the other way and I'm doing 1 hour less, right? Between 3 hours and 2 hours, that's 1 hour less, and now I have half the amount. So if I originally had 12 hours pass, but I want to have half of that amount, then it would be 11 hours, because this is happening every hour. It's not going to be 6 hours. I don't have to take half of the hours. The hours are counting up or down by 1, and every time we are doubling the amount or halving the amount depending on which direction we're going. Okay, so super important to recognize the patterns. Now, technically, we could have solved this with the equation. We could have literally taken this number, doubled it, put it in the equation, rearrange, solve for our variable, and that would have been fine as well. But that was a heck of a lot faster as soon as I recognized the doubling and the halving time. Okay. Then it says, use a graphing calculator to graph the function. A graph of this type represents exponential growth. So before I even graph it, exponential growth means literally exactly like it sounds, where the value is increasing. Okay, that's what the growth label means. And the reason it's exponential, something that we can recognize from exponential graphs, is that they're not going up by one consistent number every time. So you guys have dealt with linear relations in the past, where between 5 and 10, I'm adding 5. But then between 10 and 20, I'm not adding 5 anymore. I'm not adding 5 anymore. Okay? So there's not a consistent, specific amount that's changing. I'm going up by more every time. So this increases faster. This is called increasing at an exponential rate. Okay, so you may have heard that word before, but just not recognized that it meant that type of growth. I'm going to graph this on the internet instead, just because it's easier for you guys to see the actual graphs. So this is what it looks like when I type that equation into my graphing calculator. Is that right? No. Just kidding, I didn't actually do that one. That's for a later question, apparently. Let me actually put it into my graphing calculator then. And you guys can do the same. So I just go into my y equals. The equation is 5 and then 2 to the power of t, but we can put x. So that's why I like putting my highlighter on the page so that I know which variable is y, which variable is x, and identifying that early. And then I'm going to hit zoom 6 because, again, I can't remember what my window was last. Maybe it's something weird. So if I hit zoom 6, it'll reset my window into the standard window. And now I can see this is what my graph looks like. So it's not a straight line. As I get further along, it increases way more substantially because the more I have, the faster it's going to increase. Sure. Okay. So we used a graphing calculator. We're just going to draw essentially that on the graph. It doesn't have to be perfect, but close to the x-axis, it wasn't increasing very much. And then it started to go a heck of a lot faster. So we get that kind of slope happening. Questions? Okay, cool. Next up, so we're going to look at an exponential decay question. So just from the wording, I think you guys can gather exponential growth, I'm increasing, whereas exponential decay, I would be decreasing instead. So let's look at this example. It says there was a nuclear accident in Chernobyl, a city in the former Soviet Union. Atmosphere was contaminated with quantities of radioactive iodine. At the time, it was contaminated with 32,768 units of radioactive iodine. And then they give us some more information about what is happening as time passes. So after 1 week, how much is left, 2 weeks, 3 weeks, and so on. Okay. So with these numbers in our little chart here, it might be a little bit harder to tell because the numbers aren't quite as nice as the ones in the previous example. But every time, my number of weeks is what T represents, goes up by 1, what is happening to my amount of radioactive iodine?
Dividing by 2.
Yeah, this time it's going with division going down. So we're dividing by 2, we're halving it instead of doubling it. Okay. So same as last time, I'm going to use my highlighter to differentiate the variables, figure out which one is which. I'm going to represent T with the pink again, just like I did in the last question. So T represents the time in weeks. And then N of T this time is the number of units of radioactive iodine. Okay, so it doesn't represent bacteria cells anymore, represents the radioactive iodine. Okay. And then again, you don't really have to do this in these questions, but I like to early. Y would be N of T, and X would be T. Okay, determine how many units of radioactive iodine were left after 14 weeks. So again, in a question like this, 14 weeks represents T, that's my time. So I know T in my equation will be 14. And then I am looking for the units of radioactive iodine, which is N of T. I have an equation that says N of T is equal to that 32,768 multiplied by 1/2 to the power of T. But now we know that T is 14. So we're plugging that into the equation. We don't even have to rearrange. We can just type that into our calculators and see what we get. I'll give you a second to try that on your own. And when you type it in, you should get 2 as your answer. It decreased fairly substantially after that 14 weeks. This time we're talking about units of radioactive iodine, so I'm going to put 2 units. Okay. Then it says after 6 weeks, there are 512 cells. How many weeks will it take to double that amount? So again, we just have to be careful and pay attention to our question. And again, you could solve for this using your equation and just using actual numbers. You know what double 512 is, or you could figure it out pretty easily. So you could use your equation for this, but there's a faster way because I know that every single week that goes by, I'm cutting my number of units in half. Okay, so if I want to have double the amount that I have currently, then I actually have to go backwards, right? Because every single week I'm cutting it in half, I'm getting smaller and smaller. So if I want to have something bigger, I need to go to the previous week. So in 5 weeks, it would have been double that amount. And then after 6 weeks, after another week passes, now I have half of that. Okay, so that's how I can do double. Now, if I want half, that's the direction it's going. As time passes, I'm literally getting half every single time. So if 6 weeks is my starting point that I'm considering here, then 7 weeks is going to take me to half of that. questions? Okay, and again, if you don't see this, this doesn't come into your brain easily, you can literally always use the equation that was given to you, so not a problem. Okay. Then it says we want to graph with this window. We'll do that quickly. So go back into your y equals first. Type in the equation, which had our big 32,768. We were multiplying it by 1/2 to the power of x. Okay, so that's what it looks like in my y equals. And then before I hit my graph button, this time I'm not going to do zoom 6 because I don't actually want the standard window. I'm going to hit the window button, which is right next to the y equals. And whenever they list out a window like this horizontally, which is always how we phrase it, we just list the same order in our calculator. So on your calculator, the x minimum comes first, so we use the number that they have first for x, which was -2. Put -2 instead of -2. I don't know if it'll make a huge difference, but we'll do that. Then 10 and then 1 is the scale, which is already what's there. So those are all my x values listed as the first 3 numbers from the window. Then they tell me the y window, which are my next 3 numbers. I need a y minimum of -30,000, a y maximum of 64,000, and then a scale of 1,000. So whenever they're telling us the window, they're always telling us those 6 numbers, 3 for x and 3 for y. And now that we have those plugged in, we can just hit our graph button, and then we can see the graph and the scale really nicely because they helped us out with that feature. So this is what it looks like. We can see it has a similar kind of shape overall. We're just moving in an opposite direction because we're no longer exponentially increasing, we're exponentially decreasing. So then when I graph this one, it'll look something like this instead. Okay, and you always put the arrows on the end to indicate that it's going to continue moving in either direction, even though we can't see that on the graph. So exponential decay, I'm sure you can imagine what we just talked about. We have a decreasing function instead of an increasing one, like growth. Okay, questions? Okay, let's go to the next page. So what we were just looking at was 2 exponential functions. Depending on the value of the base and the value of what's called the a value, we might get an increasing function or a decreasing function, and we'll talk about more of those details literally throughout those lessons, how to tell if it's going to be increasing or decreasing, and what the values of a or b change about the function. But our exponential functions always need to be in this kind of a format, where there's some number a, whoops, I didn't want my highlighter, some number a that's multiplying with your power. Okay, so y and x are just your variables, b is the base of the power, and a is just some extra number multiplying out in front. All of those little pieces have specific traits and what they do to the exponential function, so we'll look at that throughout this lesson. So our first example here, we have 2 different exponential functions. We want to know the value of a and b. So up above, I just put the value of b, which was the base of my exponential function. That is whatever is attached to the exponent. I shaded that in pink, so I'll do it again here. In this question, the thing that's attached to the exponent is the 2. So that would be considered my base. That would be considered the b value. So for the first one, it's 2. That one's easy to see. But then the other one that I put in blue up here, the a value, that's supposed to be the number that's multiplying with the power. But if I look down at my exponential function, what number is multiplying with this power? 1, good job. Not 0, because if it was 0, then we wouldn't even have a power at all. We can sneak a little 1 into there because 1 times 2 to the power of x is still the exact same thing. So if there's no a value distinctly written, it's just 1. Okay, so my a value is 1 for that one. And then I have my other function here. This guy will do the same process. So you're looking at what is actually connected to your exponent. Your exponent is connected to the brackets, so it's connected to everything inside the brackets. So my base is 1/2 this time. Okay. And then again, for the a value, I need some number that's multiplying in here, but there wasn't one written, so again, we can sneak in the number 1. Okay, so there's my a and b values for each of those functions. Then we have a little table of values. We're going to do it specifically for y is equal to 2 to the power of x. They give me all of the x values they want me to plot specifically. So if I want to figure out what each of these are, I can literally just take this equation. The first value that I have for x is -3. So then I just plug in an x value of -3. You can use your calculator, but we just practiced our exponent laws. We know that a negative exponent means that we can push it in the opposite direction it started in and turn it positive. And then maybe you also know that 2 to the power of 3 is 8. So now I know my y value there is 1/8. I could do the same thing with my next x value of -2. Once again, that negative exponent is going to push my power into the denominator. And then you definitely know that 2 squared is 4. Okay, and then we could keep doing this over and over again, but I'll just give you the solutions. And we would get 1/2. Anything to the power of 0 is 1. And then these ones are easy to do in our head without writing the work. 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 to the power of 3 is 8. And 2 to the power of 4 is 16. Get all these little pieces. Okay. We're going to graph it, so we'll plot the points. Some of them obviously are going to be a little bit hard to plot, like 1/8 is really, really close to that x-axis. So remember that when we're plotting points, the x value is our horizontal axis. That's how far we're moving left to right. And then our y value is our vertical axis, how far we're moving up or down. So if my first point is -3 and 1/8, I'm going to go over 3 spaces to the left on my x-axis. That will take me to a -3. But then I need to go 1/8 on the y-axis, which is like just barely above the x-axis. Okay. I know it's not going to be perfectly accurate. Just have it a tiny bit above the x-axis, and then that should be fine. The next one I have is -2 and 1/4. Honestly, it's going to look like it's pretty much in the exact same spot on the y-axis because we're so close to it that that's fine. Next one is -1 and 1/2. So this time I can move it up a tiny bit. Then I have 0, 1. So now I'm finally at an actual grid line for my y-axis. And I have 1, 2. So I'm slowly moving over 1 every time on my x-axis. Then I have the point 2, 4. Then I had 3, 8. And then my point after that is 4, 16, which is just not going to fit. I only go up to 10 on this scale, or 11, I think. So I can't get any further than that. So now that we have all the points, we can slowly form ourselves a little bit of a line and try and just match the general slope of connecting those points. Now, something to be careful of, which we haven't really talked about yet, when you draw your line out to this side, do not let it touch the x-axis. So it's not actually going to keep decreasing underneath it. It's going to stay floating above the x-axis, and we'll talk more about that very soon. Okay, so there's my little function. I'm also going to label it because I am going to put another function on here. So this is the one that's y is equal to 2 to the power of x. And then next we're going to do the 1/2 to the power of x. So I go back. My next little table of values here has the exact same values for the x. So the first one I'm going to use, -3. I take my equation, I plug in an x value of -3. Okay, once again, we know that negative exponents means we're moving things to the bottom or the top, going in the opposite direction. So if that 2 is already on the bottom, if I want to turn that exponent positive, then the 2 is going to move to the top. So it would be 2 over 1 to the power of +3, but do I really need to put the over 1 part if it's just 2 over 1? No, right? 2 divided by 1 is still 2. And then I get 8. Okay, and again, if you don't know this, you can literally just type it into your calculator, but it's good to use those exponent laws because you will have to solve things algebraically as well throughout this unit. Then I have my next x value of -2. The same thing happens where I can pull that 2 into the numerator and then turn my exponent positive. And then we get 4. And then I'll just help you fill in the rest of them. Anything to the power of 0 is 1. And then those ones we're just applying the exponent into the denominator. And there we go. So now we have another set of values that we can put on our graph. The first one is -3, 8. So I'm going to go over to the -3 on the x-axis and up to the +8 on the y-axis for my first point. So it's mirroring the other point that I had from my blue function. It's just across the y-axis. My next one is at -2, 4. So once again, I'm mirroring the point. It's a reflection of that previous point I had in blue. Then -1, 2. Then 0, 1, which is the same point that I previously had on my other function. And then I get into the fraction ones, which are a little bit harder to plot. The first one is 1 and 1/2. So that one's not too bad. We try and put it halfway in between. But then the next ones, they get really tiny. So as long as they're hovering above that x-axis, then it's fine. Okay. And then we're going to do the same thing where we get to connect the points, but make sure that that line stays hovering above your x-axis. So when I join all of these together, it's going to trail off in this direction and hover just slightly above that y-axis. Arrows in both direction, and then we'll label that this is 1/2 to the power of x. Okay, so just like our experience last time, we can see that when I have a base that is bigger than 1, I get an increasing function. When I have a base that is smaller than 1, so 1/2, I get a decreasing function instead. Okay. All right. Next, this is what I was alluding to before. It says an asymptote is a line whose distance from a given curve gets closer and closer to 0. So what that means is we consider the x-axis in our exponential functions to be a horizontal asymptote. That happened on the screen. That means that these little graphs, these little functions are going to get really, 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 really close to that line, but they will never touch it. Okay, so as the function gets further and further along, that gap is going to keep closing and closing and closing and closing and getting closer to 0, but it will never actually get to 0 and they will never actually touch. Yes?
With the blue line, we're graphing it because it's a 2 and it's a positive, it goes in the positive way of the line. And since it's the 1/2 with the pink line, it would be a negative when graphing it.
Yes, you betcha. Yep. So that's the difference between our exponential growth and then exponential decay functions is their bases. And we're actually going to talk later about what happens when we change the a value because that will have an impact on them as well. But yeah, absolutely, the bases will change the direction on them. Good. So that's our horizontal asymptote, getting really close to that line, but never actually contacting it. So now that we know that, we're going to fill in some information about both of these graphs. Just a reminder that the domain of a function is how far we can move left to right. So domain works with our x values. It's how far can we go and spread horizontally, whereas our range works with our y values. It's how far we can move up or down. So if I look at each of these graphs, my domain, this little arrow indicates that I can keep moving to the left forever, okay? And then this little arrow at the top means that I'm going to keep moving to the right forever. Now, I understand that the one going upwards this way is not moving out to the right nearly as fast because now it's starting to increase really high, okay? But it's still slowly moving to the right. So I can go to the left and to the right forever on that graph, which means when I say my domain, I don't actually have any restrictions on it. Sorry, I'm just going to look at what color I used. I don't actually have any restrictions. So when I set up domain, I always do a curly bracket. I put an X to indicate that I'm talking about the X values. How far can I go from left to right? I put this little line down. So that's just me saying, I'm going to talk about X, put a line down, and then you talk about what X actually can do. We know that there's no restrictions on X, so that means X is a member of the reals. X just has to be a real number. That's it. Just has to exist. But it can be any value, positive or negative, any direction. Okay, so when we have a domain or range that can be anything, this is the way we're always phrasing it, where we set up our variable, and then we say that the variable just has to be real. Okay, so we learned this meaning in our set theory unit, so it's an element of or a member of. Okay, good. Now, I'll just do each like column at a time. So if I look at the domain for the other one, it's the same, right? I can move to the left as far as I want. It's going to go up a little bit faster, so it won't move to the left quite as substantially, but it'll still go on forever. And then to the right, it's sailing on really fast to the right. So we get those values going forever, which means that my domain for the exponential decay function is the exact same. Oh, that was not a nice curly bracket. Let me try that again. So still talking about x here, and then x is still just real. Beautiful. Okay, make sure we're taking notes and not on our phones, please. For the range is the same concept. It's just with the y values instead, seeing how far I can go up or down. But with the range, this time I have a restriction because my blue graph is never going to touch that axis. It is never going to make contact. It's never going to go underneath it. It is always going to stay floating right above the x-axis. Okay? Now, the value for the x-axis, I'm just going to label it over here. So our x-axis, this is where y is equal to 0. Right? The y value on that x-axis, I haven't gone up at all, I haven't gone down at all. That's where y is equal to 0. Okay? So when I need to do my domain for that, or my range, sorry, for that function, I can set it up the same way initially, where now I'm talking about y instead of x. Okay? But this time my y has a restriction. I have to be above that x-axis, and we know that that's where y is equal to 0. So that means y has to be greater than 0. I need to be a little bit higher than that y-axis, and then I can keep going up from there. And then, just like we did for the domain, we still need y to be a real number. Still has to be a number that exists. Okay, so we put both of those features in. Now, I'm not actually going to scroll back up to it, but you guys can see it on your picture. The other graph is the exact same. Okay, it still has to be a little bit above that x-axis, and then it can go up from there. So the range is going to be identical. Okay, so we have the domain and range done. Then for my x-intercepts, we know that the x-intercept is where the graph touches the x-axis. But we literally just talked about how this graph is never going to touch the x-axis, so I don't have an x-intercept for either of those because my range has to be above the x-axis. if I want to find my y-intercept, I'm doing the same thing with the y-axis instead. This time, both of the graphs do connect with the y-axis, and they actually hit in the same spot where y is equal to 1. Okay. You could list the y-axis as a coordinate point if you wanted to. I would rather you just say like 1 or y is equal to 1, because then you won't accidentally make a mistake and list them in the wrong order. So this helps to make sure you're not going to make a little mistake on it. Equation of the asymptote. So we talked about the asymptote already. We know that it is not allowed to touch that x-axis. And then I already introduced you to the concept that the x-axis, that's where y is equal to 0. So if I want to say the equation of the x-axis, I don't get to just say the words x-axis. I have to say y is equal to 0. That's the equation for it. Okay? So when we need the equation of the asymptote, that's where y is equal to 0. And it's the same for both of them. And then I'll just put in brackets. That means the x-axis. I feel like I've said x-axis 45 times in the last 5 minutes, so that's fun for me. Okay, then it says we want to figure out if they are growth or decay functions. We've already talked about for both of these. The first one is a growth function because I am increasing as I move from left to right, whereas the second one is a decay function because I am decreasing as I move from the left to the right. Questions? Okay, beautiful. What time is it? I just want to see how far I'm going to get today. We have barely done anything, it feels like. Okay, cool. Now let's look at some more stuff. This one we can do a little bit faster now that we're getting used to exponential functions and hopefully remembering how graphing works. I don't need you to put all of these into your graphing calculator. I'm going to do it for you, and in fact, I already have done it for you. So the graphs that they want, first is y is equal to 3 to the power of x. That's what it looks like on my screen right now. So if we zoom in a little bit, we can see that it has that same kind of shape as our previous exponential functions. We can see it is a growth function, and then we can see it is intercepting the y-axis at 1. Right? This is halfway in between the 1 or the 0 and the 2. So that's at 1. So if I go to put it on my graph, actually, I'll show you the y is equal to 10 to the power of x before I try and draw the picture of it. So, oh, is it going to let me? There we go. So there's my y is equal to 10 to the power of x. It's the blue graph that just came in. So we can see it still has the same general shape, but then it gets higher faster, right? We get that sharper incline. We can also see they have the exact same intercept there. Okay. Now, I guess I'm going to just show you all of them at once. If I do the next one, do we have any predictions of what it will look like? Will it be a growth function or will it be a decay function if the base is 1/3? Yeah, decay. Okay. So it'll be in the opposite direction. Let's have a look at it. There we go. So it looks like decay function looks like it's a mirror of the green graph that we have on there, and it has the same y-intercept. Okay, if I do the next one, it should also be a decay function, a little bit steeper, just like we got with the 10 to the power of x. Now we have 1/10, so that steepness is still the same. We're reflecting them over that y-axis, and they all have the same intercept. So I'm going to put it on this graph. Now, this does not have to have the exact same scale as I had in the previous picture. So the way I'm going to draw it, I want you to try and copy down as best you can because it's going to leave us space for stuff to do later. So the first one I'll start with is y is equal to 3 to the power of x. So this is the one that went out a little bit wider than the one with a base of 10, but it's an increasing function, and we got to make sure that it's going to go through that y-intercept of 1, so that's literally why they labeled it for us on the graph. And then it'll go up somewhere like that. So try and get it kind of halfway or even further out to the right, just so we have space for the other ones to draw in there. And you can put your little arrows on both sides. And I'm going to label this y is equal to 3 to the power of x. Okay, when I do the next one, that's the one we saw was also a growth function, so it's going to go in that same direction, but this one is going to be steeper. Okay, so it should be coming closer to that y-axis. This one is y is equal to 10 to the power of x. It doesn't have to be perfect, so something like that is fine. Okay, then the next one we did was a decay function. This guy was a mirror image of my graph in pink, so I want to try and get them to kind of be in the same spot if I can, just on opposite sides of the y-axis. And going off in that direction. Gotta make sure you have brackets around your base so that you can see the x is attached to the entire fraction and not just to the numerator. Then the next one I have, we knew it was a little bit steeper. We knew it was a reflection of our growth function on the other side. So somewhere around there is good. Okay, and beautiful. Those all look fabulous. It says the value of b affects the steepness as x increases. So we saw when we increased the b value from 3 to 10, the graph got a whole lot steeper. Okay, so we're going to say for that one, when b is greater than 1, the curve increases more sharply as b increases. And the reason it increases is because this is a growth function. It's going to get higher faster. Then when we're dealing with our b value that's less than 1, so when it's a fraction, as soon as the b value decreases, meaning the denominator actually gets bigger and bigger, then the graph is also going to decrease at a faster rate. So once again, it's going to be a steeper graph. Okay, so it's just telling us that we can compare these functions. If we know the b value, we know which one should be steeper and which one should not be. So if I gave you information about these two graphs and I told you that b is bigger, so let's say these two for example, if I told you that my b value is bigger than the other graph and their growth functions, then I should be able to pick out which one is which on the grid. Okay. And then we have two more that we have to do that they're introducing to us here. So one of them, y is equal to 5 to the power of x. Now, this is an example where we would be able to do this without our graphing calculator. I don't have to show you this one on that website. We should know where this fills in based on the other growth functions that I have. So I know it's a growth function because my b value is bigger than 1. And then I know that the steepness is going to be somewhere in between the 3 and the 10 as bases. So honestly, as long as you put it somewhere in between there, I would be happy. There is our next function. Y is equal to 5 to the power of x. And then I'm going to just do my other one in the exact same color because I'm running out of options here. With this one, it wants us to do 0.2 to the power of x, but 0.2 is the exact same thing as 1/5. So we are about to get a graph that mirrors the one that we just put on because that was 5 to the power of x. This one is 1/5 to the power of x. So this is going to be a decay function in between the other two decay functions that we've already graphed. And I should label it as 0.2 because that's what they did. Okay, but it's the same thing as 1/5 to the power of x. Questions? Okay. I don't need to verify the solution. I know I'm brilliant, and that is correct. Next, state the x-intercept for each of the graphs. X-intercept, do any of these little functions touch the x-axis? No, they shouldn't, because once again, these are exponential functions that have a horizontal asymptote at the x-axis, meaning they will never touch it, and that's why I intentionally put my lines floating above there. They got really close, but they did not touch it. So for all of these, there's none. There's no x-intercept. It ain't there. For every single one of those graphs, they cross the y-intercept at 1. Okay. Domain for all 6 of them, they can go left to right as far as we want. So the domain is just like the one we had on the previous page. It's just real. Okay, and domain is with our x variable, so making sure we write that up front. Range is the same for all 6 of those as well because they all have to stay above the x-axis. We can't touch that x-axis, which is the same domain or same range, sorry, that we had on the previous page, where y just has to be greater than 0. We're above that x-axis. And then the equation for the horizontal asymptote, we know that the asymptote is at the x-axis, just like we talked about on the last page, just like we talked about again here. And we know the equation for it, which is what they're asking for, is y is equal to 0. Questions? Yeah. Sure. Is that enough? Yep. Okay. So we can see these exponential functions have a lot of similarities. Okay. Wonderful, wonderful similarities. It's going to make us easy to predict what they look like and easy for us to figure out information from them without really having to think too hard or without even having to graph them. If I know it's an exponential function, I know the domain. I don't have to look at it. The domain is always real. Okay. There's one thing that we haven't talked about yet. I'm going to skip this for now because the one thing that I want to look at before I give you some time to work is what happens when we change the a value. So that's the only thing that we haven't examined yet in this lesson is how the a value impacts the graph. We've seen what the b value can do. We see that it increases or decreases the steepness, okay, and we can see that it changes the direction, but we haven't talked about how the a value changes the graph. So all 4 of these graphs have the exact same base every single time. So 3 is attached to the x, 3 is attached to the x, 3 is attached to the x, and 3 is attached to the x. So the only thing that's changing in all of these examples, this one, what would the a value be? What's the number multiplying with that power? 1. Okay, so it has an a value of 1. The next one, the thing that changes, a value of 2. The next one, the thing that changes, a value of 5. And the last one, a value of 0.5. So we are just changing the value of a, the number multiplying out in front. Here's what that looks like. So the first one we have is just the 3 to the power of x. That's the one we saw earlier, a value of 1. But then if I do 2 times 3 to the power of x, this is what it looks like. Okay, so they have pretty much the exact same slope. Okay, the way that the graph is increasing is the same. They're the same shape, but the y-intercept is different. Notice on the first one, when my a value was 1, my y-intercept was 1. Now that my a value is 2, my y-intercept is 2. What do we think is going to happen with the next one when I have an a value of 5? What do you think the y-intercept is going to be? Oh my god, you're brilliant. Look at that. You're right. That's how easy it is. The a value is just the y-intercept. That is what is changing for us. Okay, so here, y-intercept of 5. If I put a 0.5, oh my gosh, who is shocked by this? Amazing. 0.5 is my y-intercept now. Okay, that's what's changing. Now, there is a slightly more complicated relationship with the a value because depending on the a and b value together, they can do some more interesting things, but it will always, always, always be reliable that whatever number is multiplying with the power, that's your y-intercept. If you get a question on your unit test that gives you an equation, says what is the y-intercept, you better be getting that right. That should be a 100% question for this entire class because all you have to know is that one fact. Okay? And if for some reason you forgot it, because I can relate, worse memory, that's not my forte, graph it. Put it in your graphing calculator, see what it looks like, find the y-intercept. 100% on that question, every single one of you. I want to see that on the unit test. Okay. I'm going to graph these. Well, do I want to draw them? I might save that for later so that I don't have to talk to you all class. I know it's been a long one already. We're going to just quickly fill in the table, and then we'll do the actual drawings tomorrow. So for the value of A for the first one, sorry, I'm just going to make sure my colors are the same. We already talked about how A is 1. And then the y-intercept was 1. Wow, amazing. The B value was just whatever was attached to the exponent, and so it was 3. For the next one, we already talked about the A value was 2, and the y-intercept was 2. Wow, amazing. And the B value also didn't change. It's still the number that's attached to the exponent, which is still 3. For the next one after that, we had an A value of 5. Oh my god, that's the y-intercept too. Crazy. And the B value is still not changing. Okay. And then the last one, we had an A value of 0.5. Oh my gosh, look at that. There's the y-intercept too. And B value still doesn't change. Okay, so all the way through, we just kept that consistent B value so you guys could see the difference between what the A value does to the graph. This is going to be the exact same situation when I have a base between 0 and 1. Okay, I'm not going to show you that because it'll just take a while, but that is still the case. So we're going to say yes. A is still equal to the y-intercept. Okay. The only difference is that when I get a B value between 0 and 1, decreasing function. That's it. That is the only difference, is that the function is decreasing instead, but that is still going to be my y-intercept. Questions? Okay, so now we know what the B value does to the graph, what the A value does to the graph, and then how to find the domain range, all that good stuff. We are going to go as far, I know it's a long lesson, so there's more for us to do tomorrow. I'm actually going to skip to the extension and give you some information that is just going to make your life easier. So technically, this is not part of the curriculum, some of this, okay, but this is going to save you. If you can understand this, you're going to be golden through this unit, okay. So there are some facts that happen for every single exponential function, okay. These facts, sorry, I'm just getting to this right page. I want you to like highlight this, star this, bookmark it, something. Come back to this when you get stuck because this is going to help you a ton. Now, some of it we technically haven't talked about yet. We have not seen graphs that are underneath the y-axis, which is possible. I will tell you about that tomorrow. But I just want you to know these facts because they're also going to make your assignment that we're going to do in like 3 minutes way easier. Okay, so here, the y-intercept is always A. It's fact. Okay, that's the one where I'm like, you better get 100% on that question on the unit test if I give you one like that. There is never an x-intercept for exponential functions. Every single time. There will never ever be an x-intercept because it cannot touch that x-axis because it is a horizontal asymptote. We talked about that. That's where y is equal to 0. That cannot happen. It is not going to intersect with that. Every single time, the domain is real. So if you get a question that says, what the heck is the domain of this exponential function? You say it's real every single time. Okay. The range depends on the value of A. Now, we've only looked at when A is positive so far, and then that range is also positive. Okay. We will look at examples tomorrow where A might be negative, and then the opposite happens, is just our range is negative. Okay, so we'll see that tomorrow. Yep. It is 209. There's two that look really similar, so sorry I didn't clarify that before. 209, this is the extension page. Okay, so that bullet we'll talk about tomorrow, and then we can highlight it tomorrow. Kind of the same thing for this. We've only talked about when the A value is positive. Okay, so when we get those positive A values and B is a big number, we get a growth function. So we did talk about that already. But when we get A value that is positive and B value that is small, so not actually 1 yet, it's a little fraction, that's where we get our decreasing function. So that is our decay function. Okay, and then again, we'll talk about the negative a values tomorrow, so we can skip that part. And then we talked about this already. As b gets bigger, so does the steepness of the graph. Okay, if the denominator of the fraction gets bigger, so does the steepness of the graph. Okay, so that's going to help you throughout the homework. That's going to help you throughout the unit. Those are the facts that'll make your life a lot easier. And now the ones that I'm going to get you to practice with our last 15 minutes are, I'll write them at the bottom of this page so that we can have them in the same spot. So question number 1. And then I'll just keep writing more up. Start with number 1 while I do this. Yeah, go ahead.